like difficult to follow, we may end up just going back into RStudio, and that's totally fine, but we'll cross that bridge when we get there. But anyway, okay, so text mining, what's it all about? So the first thing I want to say about text mining is that it's very cool. There's a lot you can do with it, but one of the first sort of challenges I think about when I think about working with text in general is the fact that it's unstructured, right? So typically when we think about data, we think about this sort of bottom example of superstructured data where you've got columns, you've got rows, everything's organized, everything's beautiful and clean. And that's typically what we think about when we think about, data and how do we analyze data. But with text, you kind of have a slightly different challenge where you can have both unstructured or semi-structured. Oh, just kidding. Thank you. Thank you. Yeah, I'm sorry. I didn't turn camera on for today. If that's okay, I'm not feeling too great. But the slides are what really matters. Hopefully, does everybody see challenge 1 structure as a slide? Yeah, perfect. Thank you. Thank you for calling that out, Joshua. So yes, so along the bottom is the example of structured, just like, typical database or a table as you would know it, versus text kind of presents a challenge in the structure, right? You're either dealing with super unstructured data, meaning data that has no columns, no variables, no nothing, right? It's just one long string of text, or semi-structured data like tweets where you have that open-ended string, which is the content of the tweet. A joke could be, but it shouldn't be. But you also have some structured elements. You have the handle of the user who created the tweet. You have the date time that the tweet was created. You might even have metadata about the tweet in terms of what its stats were in terms of retweets or favorites. And so that's sort of what we're thinking about when we're thinking about semi-structured. And so the first thing, we're going to talk about is how do you then turn unstructured data into some kind of structure. And the way we do this is, sorry, I'm just going to close this over here. Okay, make some room so I can see the comments as we go. So the way we do this is we have, first off, like a set of vocabulary around data structures for text. So the first thing is the document, and the document is the individual text source. It's the string of the text. So in this case, it's the content of the tweet. Everything from "there was a time" to "chilling" would be the document here. The corpus is what we call the body of documents. So if we have a data set with multiple tweets, the collection of tweets altogether is going to be our corpus. And I think I made this, even more. I forgot to put animations in here. So these two tweets together might represent a single corpus. Then we have what we call tokens, and tokens are going to be usually the individual words, and those are going to become your variables. Typically, tokens are usually, when somebody says token, by default, what they mean is one word at a time. Another way to say that would be a unigram. And that kind of starts to get at the idea of n-grams, which are when you consider a token to be multiple, a token to be multiple words at a single time. So in this case, was handling could be considered a bigram if you wanted to do analysis at that level. And people sometimes are interested. You might be wondering, why would you care about was handling versus handling by itself? What further information does that give you? Sometimes with text, it's helpful to have bigrams for a number of reasons. For example, with like negation, so cannot is, a different meaning than can and not by itself. And especially as we, I'll talk about bag of words on the next slide, but typically because your meaning is given by that each individual token at a time, sometimes it's important to have two tokens at once. So yeah, I mentioned the bag of words assumption, and maybe you guys have already heard of this before, but essentially it's sort of the underlying assumption underneath how we think about text and for most sort of basic text tasks. And essentially what it assumes is that documents are collections of words, and it also treats words as sort of independent from each other. And in order to sort of create the bag of words representation using some of the tokens and n-grams that we were just talking about, there is this idea called the document term matrix, a structure called the document term matrix, which is pretty commonly used. It's where the document term matrix would typically represent rows as documents and columns as your tokens or engrams. In the example here, it's actually showing a term document matrix. So you can see the terms are the rows and the documents are the columns. This is not typical. I think generally people use a document term matrix, but this was too good an example to not use, so I took it anyway. But you can start to see, right, like if this is your set of documents, you're now representing your individual words as variables. You will be representing your individual words as variables and your documents as your observations. And now you're sort of representing a document as a collection of words, whether or not that word was present and then in what quantity. And that would be one of the possible values that you can use in these document term matrices, which is the term frequency. So this one is using just a very basic frequency count. There is also this more complicated idea called the inverse document frequency, which measures how common or rare a token is across the corpus. You get that by taking the total number of documents, so in this case, 5 are what's in our entire corpus, and then you divide that by the number of documents containing a given term. So let's say we wanted the IDF of entropy, that would be 5/2, and then you take the log of that result. Typically, if you have a high IDF, that's going to represent a rare term. And if you have a low IDF, that's going to represent a very common term. So if you think about it, these two metrics are giving you kind of different information. And what's nice is that there's this very common metric called the term frequency inverse document frequency, which is literally just, you know, the multiplication of those two terms, such that the product of what you're getting, you know, the TF IDF metric will actually be able to tell you both in a single number what are all the words that are very frequent and common, and then also what are the words that are rare and common throughout the corpus. So I have a question. Can you explain why term frequency isn't just the number of times the word appears divided by the total number of words in the document? That is also doable, sorry, and I didn't really talk about that, but the first one is just the count. That's the example that's here. And you can also use the term frequencies as a percentage. So in this example, what is this, 6 total? Complexity would be something like 2 out of 6, 1/3, right? So 33% for complexity, 50% for algorithm, and what, 12.5% for entropy. And you don't understand the 0.5s. I'm guessing that's this. I also didn't really look at this very closely. Yeah, I wouldn't worry about it. I think, sorry, I don't know what why that equation has a 0.5 in it, but really you can just use, usually you can just represent the frequency as a count or as like a percentage for that document. I'm gonna hopefully, yeah. Catherine, did you have anything on that?
Yeah, so as far as the 0.5, basically that's a weighted average. So you can think about that term frequency as like, you know, it's 0.5 times 1 plus 0.5 times this idea of how many times the word appears in the document, divided by how many times other words appear in the document, or all the words appear in the document. So I always think of these things, that's like sort of a half and half weighted average for me. So you get sort of, you already get this like 50%, this 0.5, just because the term exists. And then this other half of that is the, well, what's the percentage of that term in this document?
That makes sense. And yeah, I think there are some fancy things people can do around weighting in general, but I haven't typically used weights too much, so apologies on that. But thank you, Catherine. That's really helpful. Any other questions on this? Okay, great. So the thing you might realize, right, or maybe you're anticipating this already, is that if you're thinking about representing these documents, and maybe these are pages and pages at a time per document, you can imagine that what you'll start to get are pretty big matrices, especially where in a situation where every column is a word. And typically what will even start to happen is that those matrices will start to get more and more sparse, because not many words will not appear in many other documents. And they may be rare even within their own document, right? So this idea of dense versus sparse matrices and dimensionality starts to become another challenge that can happen when you're working with text. And especially when we're thinking about like trying to find patterns, or trying to find you know, patterns that machine learning can actually pick up on, or things that we may want to learn. The sparsity can become a challenge. So, and as well as the dimensionality. So a lot of the pre-processing that I'll talk about next is aimed at reducing dimensionality and reducing the sparsity of these matrices, so that what we're dealing with is more informative tokens about our text. And so you may have heard of some of this stuff in the past, but the you know, in the first very easy example is something like stemming, where you're literally dropping the end of a word to its root form. So in this example, I'm going to the store. Now you've got two separate words for going and go in the original version of this sentence. Another version of this, a stemmed version of this sentence would say something like, I am go to the store. And now you've collapsed one variable, you've sort of reduced that by one variable and increased the count for go, which is maybe more informative because you don't really care about going versus go. You really just want to know, does that word appear in this particular document? But stemming is pretty, it's pretty rudimentary. It really just chops off the word. Another version of this is called lemmatization, and lemmatization is a more informed version of stemming, maybe, where in this example, we have two words, running and ran, which, you know, chopping off any part of those two words won't necessarily give you the same end token, but lemmatization works by grouping together the forms of a word so it can be analyzed as a single token. So here, it's actually based on the meaning of the word and the part of the speech of that word. And in this case, running and ran both collapse down to run, so that your final term, document term matrix, actually has 2 points for run instead of 1. And like that, there are lots and lots of things you can do to help reduce that dimensionality, clean up your word list. And as every good data scientist knows, so much of data science is cleaning up your data, and that is definitely true in text data as well. So I'm just going to run through some of these different options here as well. So we talked about stemming and lemmatization. Another big and easy one is applying stop words. So in the last couple examples, I think we had things like, you know, the, to, with, for. Prepositions and articles are often, like, among, I think pronouns as well actually, are often very commonly used as stop words, where they're not necessarily informative to the overall, depending on what you're doing, they're not necessarily overall informative to the overall meaning of your text. So a lot of the times people will remove them. So I think in this example, there are probably ones like, I think I see for, and is probably in here, off, or. Also, those things would probably disappear as you looked at your clean data. Another big thing is punctuation. And I wrote handling here instead of removing, again, depending on what you're doing. Most of the time, things like apostrophes, periods, parentheses, quotation marks, all of that is not necessarily going to be informative and will actually end up, you know, creating more dimensionality if you have, for example, the word, you know, the word road appearing with or without a parentheses as being two separate tokens. That's not necessarily what you want. You want road to be represented as just road by itself all of the time. So most of the time people will just go ahead and remove punctuation. But Neil and I on the Business Innovation Project, one of the things we sort of were thinking about was, you know, when we're thinking about how do we go into text and recognize company names, one of the things we realized is that that ampersand symbol which would typically be removed by, removing punctuation, is actually really important for, recognizing some of these company names like Johnson and Johnson, where we did decide ultimately that we wanted to keep that particular punctuation in. So I wrote handling there instead of removing. Similarly, with capitalization, again, that's to make sure that things are collapsing down to the same thing. So I think road in this example has like an uppercase and a lowercase. And when you account for capitalization, it actually appears in the clean data set with larger frequency because you were actually collapsing it together. I think similarly with county and county here, those collapse to a single county and again, have a bigger frequency and therefore a bigger signal. Another thing that might be interesting is tagging part of speech. Depending on what you're trying to do, one of the things, again, for business innovation we're trying to do is eventually capture features of new products in the pharmaceutical industry. So for us, one of the things we're going to be interested in is once we can identify companies, once we can identify the new products, tagging part of speech in nearby words surrounding the names of those new products is going to be really interesting for us. And we'll do text analysis on like, how do people actually describe these new products? Are they brand new drugs to market? Are they generic drugs? Was the change that was made just a tweak in the dosage? And to what extent can tagging part of speech help us whittle down how these new products are being described and discussed in these texts, which is going to be hopefully pretty exciting. Another thing I put down is filtering language. And for this one, it's actually really interesting. One of the first steps for a lot of people when they do any kind of text mining is the first thing they do is a quick English check or a spell check, because they want to remove words that they won't be able to necessarily work with if they're misspelled or, not necessarily an English language token. And that makes sense. Again, business innovation is like my go-to example for everything. But one of the things we realized is that filtering language in the reverse direction is actually really helpful for us, because most pharmaceutical products, the names are like insane strings of characters that would never be assembled otherwise. Adderall is not an English word. Tylenol is not an English word. So by filtering for language there, that was one of the techniques that actually helped us identify a lot of products, which was really exciting. I'll talk more about LSA on the next slide, but for LSA, that's a sort of topic model method, but it's also sometimes used to help pre-process. And then the last two are probably going to not necessarily be, I don't think they'll be too relevant for the work that you'll be doing this summer. But I did want to bring it up because it's something that our group has sort of encountered in the past, and just thought it was worth mentioning. So for transforming and coding to standard UTF-8, one of the things we've encountered is that when you're pulling text, either online or pulling text from different sources, or, even you purchase data from a vendor and it comes in a sort of, all the text comes in different formats. One of the things that can happen is strange characters, or even and not necessarily strange, but even like accented characters. And that can be tricky to work with, again, because you're not necessarily capturing, the same letter as the same letter. And so, and there's some other issues, but one of the things that can kind of help account for that is by transforming and coding to standard UTF-8. Or any kind of standard string encoding. That's probably super technical, but just wanted to, in case you ever encounter this and you're like, why am I seeing something weird? Like, I've tried doing everything else, and why do these two words that look the same not appear as the same? Sometimes that can happen at the encoding level. And one last thing I'll mention here, and this isn't something we've done, but it's something I saw presented at the RStudio conference earlier this year that I thought was kind of interesting, is this idea of feature hashing, which is, I think, an idea that came from like the cybersecurity world, where, they needed to be able to come up with hashes that sort of abstractly represented, passwords and keywords and things like that. But here, sometimes people use it in text analytics to sort of come up with these buckets of, buckets of words, and all really what its true purpose is for speeding up the computation of certain, analytical tasks or processing tasks. It's sometimes easier to use this feature hashing to represent the words in a sort of different way that makes it easier for the infrastructure and the hardware to quickly perform heavy computational tasks on that data. Does this make sense? Any questions here? Has anybody done any of this? Or is that, are people working with text in their projects? Any comments, anything? You can write in the chat or feel free to unmute as well. If nothing I'm saying is making sense, that's a real problem. Hopefully this is all making sense. Okay, cool. All right, I'm gonna go ahead and assume that I know that there are a couple projects out there that are working with text, but it's maybe a little early in the summer and maybe you haven't gotten there yet. Love a word cloud. Me too. I have a line of code for word clouds for sure. All right, cool. Then I'll move on. So once you have your data structured into your document term matrix and you have it all ready, you've cleaned it up and you're ready to start doing stuff with it, what can you do next? And really here, I'm gonna mostly go over the text specific methods at the top. So sentiment analysis, topic modeling, and named entity recognition. And then I also just, for the sake of completeness and just saying it, you can use, all the machine learning techniques for the most part, supervised and unsupervised, with these data frames set up this way. So just wanted to point it out. I won't go over that today, just because, I think we have other trainings on machine learning. And I think Brandon and Gizem are teaching a class on network analysis. I'll do a very rudimentary network in the example, but just wanted to sort of point that out. There's also some stuff with Word2Vec, but I'm not going to talk about that today because I don't understand it enough and I haven't done it myself. But if you are really getting into it and you want to talk about Word2Vec, we can do that. But everything for today is based off of a bag of words for the most part. So I'm glad everybody likes word clouds because there's another one here. So talking about sentiment analysis, with sentiment analysis, you're looking at what sentiments are referenced in a given document at a time. It's used in a lot of ways, sociology, marketing, advertising, psych, econ, poli-sci. And what people are trying to do is sort of understand and in some ways sometimes score also different texts on their sentiment, on the sentiments that they contain. So in our, I think the package is tidy text. There are 3 sentiment data sets I've worked with in the past: AFIN, Bing, and NRC. AFIN scores words between -5 and +5 on, how positive or negative the emotion of the word is. Bing does just binary yes or like positive, negative, yes, no, that's it. And NRC is sort of what you're seeing down here on the left, where it has multiple types of emotion and also positive, negative. And the thing I wanted to show you here is that one word can have actually multiple sentiments associated with it. So death, for example, shows up with anger, anticipation, disgust, fear, sadness, surprise, and also under negative. And similarly with all of these words, you'll find them represented by more than one sentiment. But that's sort of why I like NRC. It's got all of that complexity. And with all 3 of these, you literally will be downloading a dictionary. And then once you have your set of words, you will literally be doing an inner join or a left join, with that dictionary and pulling out whatever sentiment you're really focused on. The other suggestion I actually got from Neil that I have not worked with, but is a well-known dictionary and sentiment tool, is called Vader. Vader is also a dictionary and rule-based tool that I saw is specifically optimized for social media. And what it'll do is give you back, you'll give it in a string and it'll give you back a % positive, % negative, and % neutral score. Interestingly with this, like it's sensitive to things like punctuation. So if you put in, you know, a single exclamation point, that'll help boost your positivity score. 2, 3, 4 exclamation points will actually have an effect on how it reads that positive score. So that's kind of nice that it takes that into consideration, where the first 3 things don't, because they're just based on simple word dictionaries. Any questions on that? I don't know, Neil, if you wanted to add anything to the Vader part.
I mean, it's just a very simplistic dictionary, which makes it useful for social media, because let's say you want to add new words to it, you could do that reasonably easily. For example, emoji, if you feel like that's not being captured in like normal sentiment analyses, then you can probably add that rule to the dictionary relatively easily.
Which is really nice. And I think, I'm sorry, I forgot to look to see if there was a Vader package in R. I'll try to look for one, and I'll include it when I upload the notes to Teams. But I think Neil, you used it with Python, right? You've used it in the past with Python.
Yeah, but it's just because the dictionary is literally available. Like I just downloaded the actual dictionary and used it.
Okay. All right. So for topic modeling, I'll talk about two methods, LSA, which I mentioned briefly before, and LDA. The thing with topic modeling, so topic modeling in general is really great because it makes interpreting the results much easier and much more intuitive. And typically what it assumes is that each document is represented by a collection of topics, and each topic is represented by a collection of words. And the way it generates these topics and collections of words is that it applies a truncated singular value decomposition method to find words that have similar corpus meanings. And I'm going to do my best to sort of translate that the way Catherine sort of talked me through earlier this week. But from what I understand, and I'm not someone who's taken linear algebra or done matrix math in the past, so if you understand SVD, you are ahead of the game here. But my understanding is that SVD is sort of similar to principal components, where it sort of is looking for combinations of variables or combinations of columns that it can sort of extract and say, you know, this combination of words or this combination of columns is what I'm going to represent as a topic. And in that combination, it is taking weighted averages of those columns. And the nice thing about this is that, you know, if you have a column, if you have a word that's in your data set, it doesn't actually have to exclusively belong to just one topic or one of those combinations. It can appear in multiple topics. And so I'm trying to just make sure I hit all the main points on this. Yeah, so if you want to get into the math of it, we can, but I really don't want to, if you don't mind. But if you want to, we have Catherine on the call and she can help. But so what the way I think about this is, you know, what are the questions that this model is trying to answer, or topic modeling is trying to answer in general. And the way I think of it is, you know, what words are occurring in similar ways across documents. For a given word, is it, you know, or for a given pair of words, are they co-occurring in the same documents? Are they absent from the same documents? So what becomes evident very quickly is that your topic construction is really, really dependent on what documents are in your corpus. And so depending on, you know, if you're scraping tweets every day, then the topics you're going to get from that topic model are going to change continually. You'll never get the same set of results. The other thing that will happen is, or the other place that you have some control on how these topics are constructed, your primary input to LSA and LDA is the number of topics you're asking it to put together. So you can sort of specify, I think typically people do something like 5 to 10 topics. And what you'll get back is something that looks like this along the top, where it won't necessarily name the topic, but you'll start to be able to understand what the pattern is of what words it's sort of assigned to that topic. So in this case, the first one is about some kind of like trial. The second one is about violence at a church. The third one's about climate change in Australia. And the last one is about NHS and budget cuts in the UK. Which, this is exactly what we're talking about when we're talking about this. This is really nice to interpret. And so if you were to do something like this, you will probably want to like create a name for the topic yourself when you're presenting it back to the stakeholder, but then you can kind of show them these are the things that the topic model came back with that belong in this topic, which is really nice. Any questions there? Any mathematicians that really want to get into truncated singular value decomposition other than Catherine? Okay. On the other hand is LDA, and I will say, people don't really do LSA. I saw that it was used as a pre-processing step, but I have never done that really. And, I think typically as an actual topic model, people don't really use LSA too much, but LDA is really the more heavily used things. LSA, which typically uses your actual TF, IDF values, is what we just talked about, but LDA instead uses probability distributions. And instead of looking at the actual appearance or frequency counts of the individual words, instead it represents both the topics and the individual words themselves as probability distributions. So what it tries to do here is, and apologies, I'm just going to pull up my notes. It's trying to reverse engineer the recipe of topics for a given document. And so what it'll do is for each document, it tries to sort of go back and create the document word by word by first picking a topic by looking at the probability distribution of the topics in the corpus. For the topic that it picks, it tries to then pick a word according to the probability distribution of the words for that topic. And it'll continue to do that over and over and over again until it sort of creates the document and the topics that it thinks about based on the two probability distributions. And those probability distributions are what are called the Dirichlet priors. There's the alpha and the beta. The alpha is the prior for the per document topic distribution, and the beta is the per topic word distribution. Typically, if you have a high alpha, that means you have a very variable mixture of topics within that document, versus a low Dirichlet prior means each document in your corpus is not going to necessarily have a wide variety of topics. It's probably going to be few and maybe more uniform. Versus with the beta metric, the beta Dirichlet prior, if you have a high value there, you're going to expect that each topic is more likely to have a mixture of words. And if it's low, it's more likely that each topic contains only a few words. Apologies, this should say words, not topics. And what you'll get back is very similar to what we just saw on the previous slide with the different topics and the words that are in them. It's just the way it's actually generating that is slightly different here. Any questions on that? I know I kind of sort of stumbled through that a bit. And I'll actually go over like code for LDA as well. We'll do an example of the sentiment analysis and the LDA. So just so you know. Okay. And then lastly, for the techniques is named entity recognition. This has a number of other names I didn't even know about: entity identification, entity chunking, and entity extraction. But essentially what you're trying to do is find effectively like nouns in your unstructured text, and some of these methods will also assign those nouns to a category. So if it's a proper noun, it may try to assign it to a person or a place or an organization. If I think I've even seen ones for like I think the example I have is like for keywords as an entity. So that can be really interesting and useful. Here, I pulled an example. I think I took and we'll do this together, but I pulled 2 Wikipedia pages of comedians I like, Ali Wong and John Mulaney, pulled named entities from their wiki pages, and then tried to see if I could find anyone in common between the two comedians. And the only person I could find from the first blush was Chris Rock. But the example we'll do will be like 5 comedians altogether. But yeah, and named entity recognition, I will say, and I'll speak a little bit more to this. I will say some of the better entity recognition stuff seems to be in Python, at least that I think I've experimented with. I found a couple libraries or packages in R, so we can definitely do this in R, but just wanted to sort of caution that I think some of the best, and most advanced and sophisticated versions of named entity recognition seem to be in Python. All right. This is the what to Google slide. I try wherever I can to put together a slide of like, what do you actually need to like take away from this talk when you leave. And I think this is hopefully helpful. And I'll talk a little bit more here. So for each of the things I sort of either mentioned or talked about, here are the R packages that kind of I've found to be useful. And I haven't necessarily done all of these, but these are, I can sort of speak to them a little bit. And we'll even play with some of these in the live code. But for ingestion, I found a package called read text, which can accommodate actually a lot of different types of text inputs. So I think it can handle even things like a Microsoft Word document and PDFs and things that, typically we may or may not necessarily read into R. For stemming, lots of things that have stemming, which is great. And same for lemming. Text preprocessing, so Quantata is what we'll use today. I will say, so Quantata and a lot of these text packages in R, I think Quantata and TM are the 2 I can think of off the top of my head. They do have specific classes of objects that they work with, specifically around like the DTM and the tokens object, that are sometimes iffy and tricky to work with, but those classes are typically what is required to feed into some of these other models, especially with the topic models. I don't love that they lock you into that. So I think in my code, I've got an example of how to do some of the pre-processing a manual way, or how to set it up so that you can do your own manual text processing. And use, like, if you're like me and you prefer to do things with regex and have a little bit more control, that, string R and the regex talk that Taya gave earlier today is where you want to spend your time. But if you are new and you're doing especially like early exploration, Quantata and a lot of the functions that they have are really, really helpful and good. POS is for part of speech. And you'll see packages appear multiple times throughout this, and that's just because they have functions in multiple things. English language, and actually I should clarify that this package, Hunspell, actually has downloadable dictionaries. You can actually download other dictionaries of other languages, but by default it comes with English and I think 2 or 3 other languages, maybe Spanish, French, and German. But Hunspell is what I use for English language checks and spell checks. I included these, they're kind of random. The news map is just, for the most part, I'm using it in the live code as an example of news data, text data that you can pull down. Baby names and gender, I use typically, most often I think I use to actually like pull out people's names. So like if for some reason I do or don't want to pull out like, you know, the Peter Parkers or, you know, Spider-Man or what, not Spider-Man, Peter, sorry, I'm thinking of the John Mulaney wiki page, but the, you know, Ali Wong, John Mulaney, and I want to know, you know, does this thing contain, is this token a name? Maybe I want to keep it, maybe I don't. That's typically what I use baby names for. I also thought it's kind of interesting, gender, both baby names, I think, and gender actually use federal data. I want to say the Social Security Administration data, and actually have like, it comes with a whole database of what are the first names that people have been born with every year. And that can be really nice. And I think baby names is just the names, but gender will tell you, you know, Nathaniel has been used, you know, 100 times each year and it's always a boy. And like Devika, for example, has been used only out over the last 20 years and it's always a girl. So that's just kind of a nice, interesting side thing that, you know, might be interesting. And then on the analysis side, for sentiment, the one I'm going to use today is tidy text, but there are some other packages for sentiment analysis. Topic modeling, this one is tricky. So I'm using LSA and topic models. I'm sorry, LDA and topic models. But I found personally that in trying to implement them on my machine, that for some reason it required Java, and I'll like point out the code that I had to use. And apparently Java doesn't come natively on Mac. New things I learned. So I had to install Java and set an environmental variable, and then download the like development version of topic models for some reason in order to make this work. I know Catherine's team uses LDA, or Catherine's project has used LDA in the past, but I think they've used Python. So if you happen to know of a better package for it, that's great. My code will have like how to do this, but I'm just putting a big asterisk that I had some issues getting it to work. So just a little caution note there. For named entity recognition, entity is the one I'm using. I think I'll be using entity and monkey learn today. Interestingly, monkey learn is like a corporate entity of some sort. It's a company of some sort, and they actually, like when you use this package, you actually use it in conjunction with an API token, and they've got some specific, what's it called? You know, specific methods for how they actually implement it. So far, I haven't hit a limit. I mean, I've only done, you know, obviously example text so far, but I'm sure at some point, you know, there's a limit probably on how many times you can ping something like that. Entity doesn't have that kind of restriction. And I will say also, Spacey was something that kept coming up, but Spacey is also I think a native Python tool. And there is an R package called Spacey that connects to that Python tool. But I haven't quite figured out how to use Python in R, or I'm not really comfortable enough in Python yet, but I thought I'd put it down there that there is an R package to actually connect to this tool that's most often used in Python. For today, for networks, I'm using iGraph. I've also used, I think, D3 in the past. Like I said, Brandon and Gazem are doing a whole talk on networks, I think, next week. So those are the folks to talk to about network analysis. I'm just doing very, very basic things today. And then for statistical analysis, LanguageR does like stat calculations, Maxent does logistic regression, and then for visualizations, we talked about word cloud. So hopefully this is helpful. You know, if you have any questions about these things, I can try to give advice, but for the most part, you know, tech stuff is still pretty new, especially because, you know, we've talked about it, I think, in the past, but it's a pretty fast changing landscape of tools. And even Neil and I working with some of these tools, we found that every 6 months, especially in Python in particular, like for the named entity recognition, that stuff changes very quickly. So depending on what you're working with, you may just need to always keep up. But for some of this stuff on the left, that stuff isn't really going to change or go away. Anything in, you know, Quantata, string R, all of that, I would probably, I'd feel pretty comfortable that will stay pretty stable. And probably the sentiment stuff as well will stay stable. But definitely named entity recognition, we're seeing a lot of churn in that space. Okay, cool. So with that, while, if there's any questions, feel free again to throw them in the chat. I'm gonna just get set up for the next phase. And so, like I said, I haven't done this particular type of exercise before. Let me try this again. So if you're finding that, like, I'm going to try and switch back and forth. So, I'll put this link in the chat. Okay. So what I've set up here, and the link that I've included, is a link to like a live code document, where if you want to follow along with the code and sort of see if you can try to replicate this on your own machine or in Ravana, you are absolutely welcome to try. I will say that I had to download quite a few packages to show everything today, so just keep that in mind. And just in general, like, feel free to unmute. I'm gonna, for things that where I want to show you some outputs, I'll try to go back and forth between the live code site and our studio, so you can actually see some of the plots and things like that. But yeah, if that gets annoying, then I can just stay in our studio, and you guys can just, take the code at the end of the session, and we can do that. But I'll look to your feedback, because you guys are my guinea pigs for this for today. Okay, so yeah, so the first thing I'm gonna do is load a bunch of packages, and like we just went over, and hopefully this will appear. No. Okay, yes, there it is. Okay. If it's not loading, I guess by you guys just like maybe try refreshing. Yeah, so the code I'm using to do this is, and you can actually see it along line 12 there. Live code is the name of the package I'm using. Oh, great, I'm glad it's working, good. So live code will sort of set up a local, I'm so bad at the terminology of this stuff, but it kind of sets up like a locally hosted web page where, it will mirror an R Markdown or an R script from our studio. And so that's what you're seeing here. There is an additional step in order for it to get like a hosted URL like this. You have to also install a tool called ngrok at the command line. And then also once you run this line of code, it'll give you your local local port or URL, like the thing that looks like 124 colon string of numbers. That's your like local site. You have to do an ngrok step in addition to that to actually create the website. If you guys are interested in that, I can kind of show you at the end. Thank you, Neil, an IP address. Yeah, I'm glad you guys like it. Yeah, we'll see how it goes. The only downside to this is that unfortunately it doesn't show you the outputs. So I'll be running these things, and whatever messages or plots or whatever I get out here, you won't necessarily be able to see on this website, which is why I'm going to have to like go back and forth. Yes, that's really helpful, Andrew. Yes, and I actually have one of those lines later, but I didn't do it up here. But that is really good. That's probably the more efficient way to do this. But anyway, yes, so like I mentioned, I think I just went over a bunch of these packages, but Quantata, read text, Quantata text models, Corpora, Newsmap, RVest is actually, I didn't mention this one on the slide before, RVest is actually a web scraping package. And so I'm actually using that because I'm going to scrape the Wikipedia pages. It won't take very long, but just so you know, that's what that is. And then Dplyr per usual. And so what I'm going to do from there is go ahead and create my first chunk and create my first data set. And to do that, I am just going to literally manually create it. And so you'll see I've created a variable for comedian, and that's got Trevor Noah, Ali Wong, John Mulaney, Dave Chappelle, and Hannah Gadsby. And then I've created a wiki variable, which has the 5 URLs of their Wikipedia pages. From there, the next thing I'm going to do is create a function to actually go have rvest read those pages. And so in this function, all I have to do is feed it a URL. That URL will get read by this read HTML function. Then it'll look for nodes that are labeled P. And so actually, it's probably worth me showing this. Let me take an example. Let me take Trevor Noah. I'm sure you guys sort of actually already might have seen this with Biowan's web scraping, but just to reiterate, just so you can see it a second time, you know, if you are on a Wikipedia page, and I'm resizing this so it's a little bit easier to see, and you hit the inspect option, or I think you can also look at view page source, but if I'm in Chrome and inspect is what I like. And then when you see that pop out thing, there's like a little square with a mouse hovering over it, which says select an element in the page to inspect it. You can sort of hover over these different elements on the page, and I can see that the text of this web page is given by the node P. Sorry, let me hover there so you can see it. It's the purple P in that box that pops up. So when I'm looking at what nodes I want to extract, I've decided to extract the P nodes because those are really the main text of the Wikipedia article. Hopefully that makes sense. I think there is also, there are some other tools. I think there's plugins that you can get for Chrome and other things that will actually, you don't have to look at the source. You can literally hit like a little add-on here and actually, you know, pull up what the node is. You can select the text and it'll have a little pop out, so you don't have to navigate all the craziness of the inspect, but it's always good to know both ways of doing it. So going back here, so I've got my read wiki page, read wiki function. I've decided I'm going to tell it to look at P nodes. Then this HTML text function is going to specifically extract the text out of those P nodes. And the paste is just there because I think at the end of this, it gives me back all the individual paragraphs, but I really want one large string, one large like page that represents the entire wiki page. So what I'm going to do next is take that function and apply it to my comedians data set. And when I do that, so let me actually run this, and then this. Oh, shoot. Oh. Okay, that's it. Well, give me 1 second. For some reason, I'm getting like the clock thing that says pending execution instead of just actually running. But hopefully, it will just take a second to figure out what's going on. Okay, I might need to restart my R session. Give me 1 second. Okay. This again. Okay, I think that worked. Okay. Okay, there we go. Sorry about that. So now, and what I'll do so that you can actually see this is share screen of my RStudio. This. And so now you can see from my first step, right? I just created the comedian and the wiki variables, which is what you see here. In the most recent step, I now have a new variable called text, and you can see the entire text of the Wikipedia page for that comedian. So if we wanted to double check it, we can pull it up, and now we can see hopefully all the text from that page, including things like the citations and new lines that are kind of ugly, but I'm happy with this. I've got all my raw text, which I'm happy about. Let me scroll down here. Okay. So now, a couple other things that I'll do, just so that we have some other examples for other things. I wanted to show you the read text package has a couple functions. I'm not sure how much of a delay there is between live code and my script. Oh, shoot. Okay. All right. Apologies, guys. I think it's because I restarted my R session. Give me 1 second. Oh, did that work? Yes. Okay. Can everybody, is that same site working for everybody? No, it's not, is it? Oh, damn. Give me 1 second. Okay, apologies for that, guys. The new site is going to be in the chat. Looks like that. And that will have all the code that we just did so far. And some new code, which I just added, which is to just show some examples for read text. The nice thing with the quantdata object is that it actually has some sample Twitter data. So I went ahead and used read text to read that in. And again, read text can handle a number of different types of data. So it can read in CSV, tab separated Excel files. It can also read JSON, XML, and HTML. And it can also read PDFs and Word documents as well as RTFs. And so now that we've read those things in, I went ahead and printed some of the outputs of that. And for the tweets, you can see a lot of these, I think, are actually like about the UK and Brexit, or some election was happening that day. So that's what the top 9, at least, of this data set look like. I also read in like a resume that we had to submit to NIH that I submitted. So you can see like my resume text also went in, even though it was in PDF form, which is really nice. All right. So next, and I'll go back up here, and maybe I'll just leave it down here. I feel like switching back and forth is kind of annoying. So for the next part, I wanted to show you a quick like flavor of sentiment analysis. And so for that, I'm going to use the library tidytext. And with tidytext, in general, what you're going to be doing is actually downloading the dictionaries directly into your R environment. And you do that using a function called getSentiments. And with getSentiments, you want to specify which dictionary you're going to be working with. So like I said, I like to use the NRC one because it has just more information and more sentiment options. And so when you do that, what you get back is something like this, which is a straight dictionary. You know, you can see there are 13,000 words that it has in here and their corresponding sentiments. And you start to see already that, you know, the word abandon already has multiple emotions. So depending on what you're trying to do, you may want to limit down to a specific sentiment that you're interested in. So let's say, you know, we want to look at the sentiments of the tweets we were just looking at. So what I do here is the Twitter data set has a lot of variables. For the, you know, sake of ease for today, I'm just going to go ahead and only select the text variable, which is the actual body of the tweet. And we'll talk more about, you know, how to tokenize with quantdata, but just for the sake of, getting an example working. I've put tokenize word here, and I've also used the string R function string to lowercase all of the text and then tokenize it. So that would be nice if I read in the library stringer, wouldn't it? There we go. And so now what you can see is a variable called word. And in that variable word, you can see each row has a vector of all of the tokens that we generated in that step. And now we want to actually look at them so we can unnest them. And now you can see where that first row originally had a vector of 4. It now has 4 rows because we've unnested it. And unfortunately, it's not very informative, right? We've got a lot of noise in here, it looks like. So I did some things to help clean up this text. I said, make sure that the number of characters in the word variable is at least 3. Is greater than 3, so at least 4. And make sure that when you are looking at that token that there aren't numbers in it. And so what it's saying is if you detect a number in the token, consider that to be, filter it for that value is false. I think you guys just saw this string detect function with Taya earlier today, but now you get to see it actually played out and used, which is nice. And then the last thing I do, so actually let's go ahead and look at that output. So now you can see, hopefully now we have some more informative words in here. And you can see even like some of this is probably hashtags, and it won't actually bind to anything when we do the inner join to the sentiments dictionary. But we can at least trust that this is hopefully at least more information than nothing. I will say in the business innovation project, we've done a lot of cleaning of XML, badly parsed XML, and financial language, because we were pulling the SEC data sets or SEC filings, which have a lot of financial language in them. So the next thing I do is then inner join this against the sentiments dictionary, which we created up in line 57. And you can start to see now only those words that actually had a sentiment associated with them, and that they have multiple sentiments associated with them. And so the last step there, this count, is all that's doing is creating like a frequency of appearance of that word and that sentiment. And the next thing I'll do, again, another library. I'm sorry guys, I probably should have put all the libraries up front, is add in a word cloud. And in my word cloud code, I tell it that I want it to take the word from the word column from WC sentiment. The frequency is the N variable, and I'm sorry, we should look at this real quick just so you guys can see it. Oh my God. Please stop. I don't know why it's doing this. This is really annoying. Is it still running something down here? No. Okay. Well, it's working down here, I guess. For WC sentiment, you can see it has the word, the sentiment, and then the count of appearances throughout the entire corpus. And so when I tell it to create the word cloud, what it does is, I'm pointing it to the variable for word, I'm pointing it to the variable for the counts, but I'm also having it color by taking a factor of the sentiment variable. And hopefully, no, okay. I am not sure what to make of this because it was not doing this like an hour ago. Okay. I hate to do this. but I think what I'm going to do is, I'm worried it's the live code stuff. So this is what I'm going to do. I'm going to put a live code of the entire thing. So if you guys want, you can look at that. And I guess I will turn off live code on this, which is a bummer. Or maybe I'll just share the R Markdown. Yeah, I'm not sure, because then I guess if I have it running, it'd still be an issue. Okay, guys, sorry about that. I'm just gonna, I think for now, I'm just gonna run through the code, and I will send you guys the R Markdown after. Apologies. I'm hoping that's the reason, but I guess if this keeps happening, then we'll find out. Okay, let's try this again. Will that work if I just do that? No. Okay. Okay, now let's try this. Hello. Okay, there we go. Okay, so now, now we have our word cloud, and you can see vote is appearing in there multiple times, and things are multicolored because of the multiple sentiments, but this is really, really quite noisy, and you know, we don't necessarily want this much sentiment at once. It's kind of hard to tease apart. So I'm going to take, you know, the sentiment data set we just created and filter it just for trust. I'm particularly interested in looking at trust. And so now I can see, and maybe I can make this bigger. I don't know if you guys can see that. No, you can't. And actually it doesn't make it bigger, which is not helpful. So you can see in the plot, like, you know, the common words that are associated with trust. You can start to see, are these words signifying positive trust, which I think to me, for the most part, they are. I see, you know, economy, vote, crucial, lovely, brilliant, supporting. You can tell these are British tweets, I guess, because council and brilliant is, I think, probably more British style words. But yeah, just thought that would be a fun example to show. All right, so next we're gonna actually start getting into how do we create some of the data structures that we talked about in terms of the document term matrix and the tokens and things like that. So the first thing we're gonna do is take our comedian data frame and turn it into a quantata corpus object. And so the way we do that is we take our comedians data set and apply it to the corpus object. And I also add in an argument for specifying docvars, which are document variables. And I say, you know, create a variable called comedian, which takes the comedian variable. And the reason, you'd think that you could just quickly, you know, convert comedians to a corpus really quick, but unfortunately, some of the classes of these things are kind of tricky. And it's easier, it really is easier to sort of do it this way. But if you look at this corpus, it sort of summarizes at the top, you've got 5 documents and 1 document variable. And this I find is kind of a hard way to look at it. But if you take the summary of this object, now you can actually see something that's a little bit easier to look at with the same summary at the top, but then with some information about the tokens and the sentences and the comedian. Unfortunately, even though it's showing you all of this information, not all of this is necessarily available because we didn't create all of these things as document variables. So the only document variable we still have available is just the comedian one and the text itself. And if we want some of these other things that it's showing, we have to manually add those things in. But we can do that. Those are things we can do, and I'll show that in a second. But let's say we wanted to also take this, and let's say, you know, let's hope it was much bigger. But we're only interested in, you know, the subset of this corpus with over 100 100 sentences in the particular document. You can use this sort of corpus subset as well as this end sentence function, and that will actually subset your corpus, which is very nice. But now if you wanted to do anything else, like I said, the only variable that's available to you is the comedian one under doc bars. So we need to create some new variables. And to do that, I've sort of just taken a straight, you've probably seen this before, like $ created the name of it, and then straight up run the function next to it. And so this first one is getting the character count. The second one is counting spaces using regex. The next one is counting paragraphs using new lines. And the last one is counting just the number of times the word stand up with or without the dash is being applied. So what's happening here, and just again for regex, explaining regex, the question mark is saying that the previous character is optional. So what it's saying is that this dash may or may not exist there. It could be stand up as a single word or stand dash up. And now when we look at doc bars, we have more things to work with. Character count, space count, paragraph count, and stand up are the variables we have available to us. Oh yeah, I'm sorry, I missed your question. I can zoom in a bit. Is that better? I can go one more.
Perfect, thank you.
Yeah, no problem. So now that we have that, we might want to start looking for strings and patterns in our text. And we might also decide, you know, these are really big articles, really long Wikipedia articles, and maybe we want to find a way to chop those very long articles into smaller chunks. So one thing we can do is use something called the corpus segment, which is different from corpus subset. And actually, let me break this up for now. Oh my God, hello. So what we're doing here is breaking up the corpus, comedian corpus, using this pattern, which is looking for Netflix and a space followed by whatever the next word is. And I will say, by default, Quantata has its own inbuilt, more user-friendly searching method. I am more attached to regex, so I specify this argument value type should be regex, so that when it looks for the pattern, it's using regex search patterns and not the Quantata search patterns. And just, I don't know if I have an example of this in here, but for one example of the difference is that the star in regex, or the asterisk in regex, stands for like multiple, like many. But if you didn't specify regex here, then the default Quantata search uses star as a like wildcards operator, or like kind of like an any character instead of a many. So just a little nuance there. And so now when I run this command, what you're gonna see is originally we had 5 documents, but now we have 32. And what it's doing is it's taking each one of these documents, it's looking for this pattern and pulling out the text between each of these patterns. So if we look at it, and I'll show you, and I think in this example, I was showing just like a basic Netflix search. Yeah, okay, and actually you can see it here too. So you can see here, if we are looking at how it applied this to Trevor Noah, the first sentence here is on Netflix, I'm sorry, on 14th September 2017, but it kind of starts with this period, so we know that something's missing. And if we go back and pull up the Wikipedia page, I'm trying to see, I think if you literally just search for Netflix, you can see the first appearance of Netflix is here, and it's followed by a period, and then the quotations, and then the next string starts with on 14 September. So what that function did was it took this page it looked for the first appearance of Netflix, and then it's going to look for the next appearance of Netflix, which is not in a P node. So if there's nothing else in the P nodes, then it'll take everything from Netflix to the end, or Netflix to wherever it thinks the next endpoint is. And so if we go back, now we can see like it's sort of, that's where it's taking that segment from. It's ending it after the Netflix and then breaking it up that way. And it's doing that for all of these. So I think, yeah, I guess for Trevor Noah, there was one reference, so it probably took from Netflix to the end. For Ali Wong, she probably used Netflix multiple times, or somebody who wrote it, you know, whoever wrote it, had Netflix appear multiple times. So there's multiple segments that it's pulling out. And similarly for the other comedians. Does that make sense? Okay, cool. Okay, so the next thing we're going to do is, you know, we've got our corpus. We know how to, you know, filter the corpus if we want. We know how to break up the corpus into more documents if we want it. But now we've got the subset we want, and we've got the documents broken up in any way we want. And so the next thing that we're ready to do is actually generate some tokens. And so pretty simple. The most basic way to do this is to use the tokens command. And what you'll get back with this is just a straight every single individual token that Quantata can find. And we can already see some of the problems that we talked about with pre-processing. There's numbers that may or may not be useful. There's punctuation that may or may not be useful. So we're going to improve on this by adding in an argument here called remove punct is true. And now when we look at this again, the punctuation is gone. The numbers are still there, but that's okay. For our purposes, we're going to keep it in there. But all of the punctuation is gone, which is what we wanted. And the next thing we'll do, Quantata has this function called quick. And quick kind of helps you look very quickly, for lack of a better term, at the tokens for a specific pattern. And so in this case, I'm saying quickly look through all of our tokens and see if you can find anything for show or sitcom. And again, I didn't specify regex here, right? So the star is actually a wildcard. And so what this allows me to look for here, instead of regex, because normally regex would mean, you know, this would mean in regex, look for, this can be as many W's as appears. But here with the default inbuilt functionality, it actually stands for, there can be another letter after this. And for me, I was thinking of like multiple shows or multiple sitcoms. And so the results that you get back from this is it sort of tells you what where it found those tokens, and also what tokens preceded it and what tokens followed it. So in this first example, current host of the daily show is the keyword that it found based on what pattern I specified. Of the Daily Show, an American satirical news program. And then similarly, you can see, you know, where it found shows. I think sitcom is in there somewhere. Yeah, sitcom. Let's say Nick Kroll hosts a prank show called Too Much Tuna, you know. So it's kind of nice, the quick function, because it kind of like is a nice gut check to be like, does what I expected show up, and what was the surrounding context? And again, because I have a personal like vendetta against class objects that are really annoying, I'll just call out the fact that this tokens object that we just generated is its own custom object, and it is not easily convertible back to a data frame or anything else, or it is, but you just have to do a little extra. I think I have code in here for that too. To solve for the class problem, I found that this works. You can actually use per and unlist the tokens, and so now you can actually pull back, you know, the tokens as a separate object. And I actually would, if it were me, I'd actually go ahead and throw that back into my original data set so that when I'm looking at my comedians data set, I have everything in one place, the comedian, the wiki page, text, and now the tokens. And that's just because I am like maybe finicky and annoying about custom classes and things, but this lets me do more manual cleaning, and it gives me greater control versus having to rely on things like remove punctuation, which, like, as I mentioned before, I don't necessarily always want to remove all the punctuation. So having this actually helps me have a little bit more control over what I'm doing. Hopefully that makes sense. Any questions? Again, I feel like hopefully I don't see anything in the chat, but feel free to unmute at any time. And then if we wanted to look at generating the tokens, but we were interested in bigrams and not unigrams or just single tokens, you can just use another pretty simple function. I think it's, instead of tokens by itself, it's tokens underscore ngrams. And you apply that in this case to the unigram. So you need to have already generated the individual tokens first, and then specify what number of tokens you're interested in putting together. So this could be trigrams. You could do, I think you can put like 3, 4. I've never seen really people even use the 3, but you can. And when you have that, now you can see that it's actually starting to put together different tokens. Trevor Noah born February 20th. And you can already see how that might be interesting, right? Because South African by itself is a totally different token than South and African, which would have been treated separately and independent in the backwards model that we'd be using. Okay. I'm going to showcase this next thing, but I probably wouldn't use it myself, but I thought it was kind of interesting. There's also this idea of compound tokens, which is different from bigrams. And what this is doing here is actually specifying specific bigrams that you want to look for, and leaving everything else as just a regular unigram. So you can see here that it looks like nothing changed because television show and Fox sitcom, I think, were not in the top ones. But what will happen is if it finds television and show next to each other, Fox and sitcom next to each other, it will actually turn that into a compound token. And you can see that here where with these compounded tokens, you can see cast member on the ABC television show. And so this is the token, the compound token that it created using this particular phrase and pattern combination. But it might be helpful. Maybe you don't want bigrams all the way through, and maybe you only want specific bigrams. And so that's what that would be helpful for. And I've shown you a lot of cases. The quick function is really nice because it shows you the surrounding words. And there is actually like a function to specifically pull those out as well. So this tokens select is working again on those individual tokens. And this time it's looking for show and sitcom and saying, give me the window of 5 words around that before and after. And so if we run that and we look at it, now what we can see is the actual, individual tokens surrounding the pattern that we just looked for. And we can look at it in the data frame way as well. And we can see exactly the same thing we saw before, but in this case, we know that the tokens that we generated are specifically only those tokens that were 5 before and after references to show and sitcom. You guys are quiet. This is making sense, right? Yeah, I'm not like losing anybody. Hopefully I'm just I'm doing such a good job of explaining and nobody has any questions. Okay. If anybody were to just say like, yes, this is good, I could really use the validation. in the chat? Okay, great, thank you. Okay, cool. Okay, so yeah, we talked about that. Okay. So, so everything I just walked through is how to actually generate like the tokens and the corpus, and also start looking at documents in a different way. I thought I'd also show you some cool things you can do based on different kinds of dictionaries. And the first one I thought I'd pull is one from Newsmap called Data Dictionary Newsmap. Hold on. Yeah, there we go. For some reason, it doesn't work on the first run always, and it works on the second run. But Data Dictionary Newsmap English. And this one is a cool dictionary which translates words back to their regional and country association. And so you can see, you know, basically kind of is slightly nested. There's different levels. The first level is like basically like largely continental-ish. I say that because I think one of them is called Oceania. The second one is sort of like regional within that, east, middle, north, whatever. And then the third level down is the actual countries. And so when we look at what's actually in here, you can kind of already see it here, but just so you can see it again, that's what the names at the second level look like. And this is what the names at the third level look like. And these are the actual individual countries. So if we wanted to actually take the tokens that we have and start looking at what is the regional association with these, we can use this tokens lookup function again on our individual tokens and map that against our dictionary that we just downloaded from Newsmap. And here we're indicating the first level, which means the sort of highest level, the sort of continental or large geographic area level. And so when we look at that, now we can start to see for each of the comedians what are the sort of large geographic areas, continents that are associated with them. And this is slightly, maybe, hopefully what you'd expect, you know, for Trevor Noah, mostly America and Africa, though there is one reference to Europe. Ali Wong, I'm sorry, and if you guys don't know, maybe I should also explain, Trevor Noah is from South Africa. I think Ali Wong is, I want to say she's like part Chinese and part Vietnamese. So seeing references to Asia and America makes sense. John Mulaney, I guess I don't know. He's American, he's white American of some sort, but I don't know necessarily his heritage off the top of my head. Dave Chappelle, mostly America, one reference to Africa. Hannah Gadsby is from Australia, so we see some references to Oceania. Yay, I'm glad you love Trevor in Europe. I also love Trevor. So yeah, I have a question about who makes the dictionaries and how they are made. So the ones for sentiments, there are actually papers, I think, associated with each of those. And in fact, most of these, I think there are actually papers associated with them. And you can go back and look at, how, you know, what approach they took. But they're kind of all different. I think for the sentiment ones, the three that I mentioned, the AFIN, the Bing, and NRC, I think those are all like academics who originally started them. This Newsmap one, I'm not terribly sure about, but I'm sure it's somebody made this package and did some kind of decomposition. I will say, like, at least Neil and I have been making dictionaries for some of our projects over the last year. So like we've made one for like cleaning up XML, like badly parsed XML, and we've made one for like pharmaceutical language. We've made one for financial language. And it is just like a really manual, terrible process. I mean, it's just like, you have to kind of do a lot of manual individual review. So I'm not sure necessarily, I don't know that other people have like a more automated way of doing it. It's kind of a terrible process. But I think sometimes you might not even necessarily want things to be automated for dictionary construction, just because so much of the way we use words is so, it's so annoying. You know, we'll have words that mean 3 different things and in different contexts, you know, may or may not be appropriate to focus on or remove. We have words that are totally made up words and, you know, just didn't exist in the dictionary. So, you know, at least for my personal experience of creating dictionaries, that's tough. And I think, to be honest, I haven't read any of these papers. I think most of them come out of academia, if that's helpful. And I can look for those papers and send them along if that's helpful. But yeah, so this is what we're seeing for the regions makes sense. And if we want to go a level deeper, we can, and we can actually look at the countries that are specifically mentioned or associated with tokens in this set as well. And if we look at those, I think ZA sounds for South Africa, so that makes sense for Trevor. CH is actually Switzerland, so that was the Europe mention probably, because I think his father is Swiss. For Ali Wong, we see Vietnam, as other than the US. John Mulaney has South Africa. I forget, I think IE is Ireland. France is in here, Dave Chappelle. Oh shoot, I forgot what RE was. Dang it, but maybe it'll come to me like half an hour from now. And then Australia and Canada under Hannah Gadsby, which is great. So just kind of an interesting thing. You could probably make a network out of that as well and be like, have they gone to the same places, or do they have the same mentions of the same places in their wiki page? But speaking to what I just went over, we can also actually make our own custom dictionaries if we have things we're really interested in. So in this example here, I am making a dictionary where I say, if you find the words ABC and Netflix, translate that to TV. If you find the words stand or improv, translate that to comedy. If you find the words pet, daughter, or son, translate that to children, because pets are children too. And we can apply that custom dictionary using the same tokens lookup we just used. And what we'll find when we do this is, you know, only those tokens and their decomposed categories that are associated with that particular word. All right. Okay. What else? What else? Okay. So for the next thing, forget, I'm just trying to remember what I am doing here. Yes, so, okay, so for the next thing we're doing, we're actually gonna go ahead and create our document term matrix. And to do that, we will use code that looks like this. So we're taking our original corpus, we are creating tokens without the punctuation, and then handing that into this DFM function, which is going to actually generate our matrix. And when we look at it, we can see, you know, we've got 5 documents, 5 documents, 5 doc vars, the original doc vars that we created earlier in this training, but also tons and tons of features. So 2,000 plus, almost closer to 3,000 features, meaning 3,000 words. And it also will give you like a rating on the sparsity of the matrix, which is really nice. And we might decide that, you know, we kind of like this, but we want to see if we can get some of the noise out of here. So I'm going to add 2 more arguments on top of this. I'm going to say, add this DFM select and specify the pattern as English stop words, and say, select this by removing it, which essentially I think it's weirdly phrased, but what it's saying is remove stop words. And then this last one is looking at numbers. And I said, you know, if you find numbers in the token, like go ahead and remove those as well. And so if we look at this now, we got a slight reduction in the number of features and a slight boost in terms of the sparsity. So I think it was something like 2,700, now it's 2,500. It was 69% sparse, now it's 72% sparse, which is great. So the other ways that we can use to reduce sparsity from here is a set of functions like this. So top features is going to take the top 50 words by frequency. And so if you take that, these are sort of the tokens that it says are in the top 50. So that makes sense. This is probably Comedy Central. You know, some of these may or may not make sense, but yeah, I guess Comedy Central, Netflix makes sense. Stand-up and special, comedian film, Emmy Award, all of that's what we'd expect to see. The second one is limiting by a threshold. So in this case, it's saying the token needs to have at least a minimum term frequency of 10. So, and that's total across the corpus. So now we've gone down from what, 2,700 or 2,400 features to 82. So just kind of an interesting thing there, but so that may or may not be useful, but just so you know, there's other ways of sort of limiting this down. All right. One thing that I just thought was kind of interesting, I found this statistic called lexical diversity that I thought was kind of interesting. And this is going to be a statistic that would be at the, I think at the document level. And when you calculate that, it sort of gives you back a metric of how diverse the words are that are used in that particular document. So Hannah Gadsby has the greatest number of lexical diversity, meaning the most diverse collection of words. And then it goes next, I think, to Ali Wong, and then to Trevor Noah, then to, I think this is John Mulaney, and then Dave Chappelle. So that's kind of interesting. It might help you understand how different are your documents from each other and how diverse are the words that you're seeing within that document. I also saw these other document level metrics that I confess I just thought they were kind of cool. This text stat distance sort of calculates a distance between the terms. Hold on to that. No, I didn't run the last one. Between the documents in terms of text. And I think I have to pop this into a new share. Can you guys see this better? It's kind of iffy to look at, but essentially what text distance is sort of showing you is whose text is more, which text more closely resembles each other. And so Ali and Hannah are kind of closer than John Mulaney, then Trevor, and then Dave Chappelle. So just thought that was kind of interesting. Let's go back. Let me close this. There's also something called keyness, which sort of takes all of the documents and compares them against a single document. It's kind of hard, man. If I can find a way to get live code to show output, that would be ideal. But in the meantime, you'll just have to struggle with me. And so in this case, you can see it's sort of measuring the other four comedians' text against Trevor Noah and sort of saying what are the keywords that sort of uniquely identify Trevor Noah, and then what are the things that are sort of set apart in the reference for documents. Again, I might not use this, but I just thought it was interesting. If you have one document that you know is a control, maybe, and a few others that you know are specifically, for us, maybe it's like, maybe we have a document that's not labeled as having any innovation or new products, and then we have reference documents that do, or vice versa. Maybe we want to compare what are the keywords in those. Yeah, maybe. So I have maybe a question about detecting plagiarism. I think for plagiarism, some of those algorithms are probably even more intense than this, because this is really looking at one word at a time. for plagiarism, you'd probably want to detect larger swaths at the same time. And I think they even do things like, you know, how it's probably sort of similar to string distance. I didn't talk about this today, but for string distance, you're looking at the distance between how different two words are. So let's say you have the word, oh my God, let's say you have the word is and as, is and as, that would have a string distance of 1 because it's one character that you would need to change to turn one into the other. And I think some of those plagiarism detection algorithms are even more complex in terms of they can look at a paragraph and see how much of this paragraph would you need to change to get to something else. So they can say, you know, only, you know, somebody copy pasted this in and, you know, they changed 2 or 3 words. And so the distance of this paragraph to something that I know existed before the due date of this paper, you know, there's a higher likelihood that this was copy pasted and then a couple things were changed. So yeah, hopefully that was helpful. But yeah, that stuff is really interesting as well. All right. Sorry, I'm just drinking a little water. Okay, so for the next thing, I think I'm gonna maybe skip that. Okay. Okay, so for the next thing, I'm gonna run an LDA model, but to do that, I will just very quickly show you the mess that I had to make before I did this. I'm sorry, wait, is that right? I'm sorry, no, that was for the entity thing. Okay, never mind. So sorry, for LDA, I ended up having to use code that was similar to what I think it was Andrew posted earlier in the chat about installing multiple packages at once. I just found that I couldn't, for some reason, I think the topic models package from CRAN, I think it was not compatible with our version 4, which is what I have on my personal machine. And so I had to go to the source, but then installing directly from GitHub using dev tools like this, and then doing like Tricker / topic models or go whatever. It didn't work, whoever the source of it was. And for whatever reason, I found somewhere, I think on Stack Overflow, or maybe it was on the GitHub repo itself. They said this is the best code to use, and this is what ended up working. Not 100% sure why, but this is what works. So I think it's whatever the source here is, the topic models to LDA viz. This is what ended up working. I'm sure Catherine can speak to libraries in Python that do it much better. And I will say that for whatever reason, this took a long time to run as well. So take that with a grain of salt. Luckily, I think I've already run it. So yeah, it's still in there, which is good. But the first thing I have to do is, oh shoot, and actually I did have to, sorry. Let's, okay. I'm sorry. So before I do this, before I actually do the topic models, I actually went and created a new data set using news from The Guardian. And to do this, I think this, oh, I probably already have it, didn't I? Yeah, okay. And this data set has 6,000 documents and 9 document variables. And I decided to subset it for only those documents that were published after 2016. And then I look at my number of documents and it's still 6,000. So go figure. They're all relatively recent, which is good. Then I decide to go ahead and make my document term matrix. I remove my punctuation. I remove my stop words. I think some of these things are just, you know, again, adjusting for frequency counts and also removing some of the words that appeared pretty frequently in these articles. So time updated, the time zone. And then this last step is saying, you know, it had to have more than 0 tokens, which makes sense. Probably, oh my God, I probably don't need to rerun this. See, hopefully, yeah, okay. And if I take an example of one of these, you can see that this particular one is not a good example. You can see the actual text of this particular article. It starts with Australia's Education Minister, Christopher Pyne, has vowed. I think this one is about the climate change in Australia. And so the first thing we have to do is convert it to another format that's used in order for the topic models to run. And this function convert is in Quantata, but works to convert it to the format it needs for topic models. And so if we look at that, it's got our documents. And if we look at, I'm not going to run this just because it took like 5 to 15 minutes to run last time. But what I'm doing here is running the LDA topic model on my document term matrix and specifying a number of tokens, or sorry, a number of topics that I want. So I want it to generate 10 different topics for this particular corpus. And if I go ahead and look at five of the terms for each of these for each of the topics, you can start to see, this is actually what I included a screenshot of in my slides, but you can start to see the words that it selected for each of those topics. So something about customers and sales for topic 1, topic 2 is about Syria, topic 3 about a town woman's son dying with friends, I guess. And then topic 4 we saw before, topic 5 seems to be about the election, topic 6 about maybe the financial situation in Greece, et cetera, et cetera. And so, so you can start to see that it's sort of assigning those different words to the topics. And if, we wanted to, we could change what documents we were including in the corpus, or we could change the number of topics. I know Catherine was telling me something about some of these packages for LDA require you need to set a seed because they do some randomization in order to improve the speed of the computation. Catherine, if you're still on and you want to call me on that, that's totally fine. But so one thing you may need to think about, not for this particular function, I don't think, but just in general, is whether or not you need to set seed before you run this if you want to, try to generate the same thing every time. But it can be tricky depending on the package and how it's been implemented. Okay, so that's an example for LDA. I think I've got just about half an hour left. I think we'll be finishing probably in the next, 5-10 minutes. So we'll have time for any questions or comments at the end. But the next thing I will show is some of the entity recognition. And so for this, the libraries I'm going to use are, I think, Entity and Monkey-Learn. And this is, okay, so this was the thing I was talking about before where things for some reason got really weird with Java. So for this, so I used the library entity. I think that part was fine. This person entity, yeah, so you can see if I try to run person entity before I've set this system environmental for Java, there's an issue. It says, it can't find Java. And so when I encountered this the first time, I had to first actually go to like the Java website, download Java, because on Mac, it just does not come with Mac. And then the second step is I had to figure out where it downloaded Java to, and then set an environmental variable pointing Java to Java_home to that folder location. And I found that once I set that system environmental variable, then entity works. And I'm pretty sure the same requirement of Java is true also for OpenNLP. But I don't have an example of that one for today, but I thought I'd mention it because it was annoying and weird. And if you're on a Mac, you will also be annoyed and weirded out. But you can start to see already that that it's pulling out people, right? Sorry, I probably should have saved it, but we'll see it here. So now I'm running comedians people and creating a variable that will actually have hopefully people's names for each of these comedians from their Wikipedia page. And so different numbers of people, 59 up to, there's 15 all the way up to 135. And if we look at one of those examples, and maybe we'll start with Hannah since hers is a little bit more manageable in terms of the number of people, we can see a mix in terms of what we're getting back. So some of these are actually people. Some of these are actually like a person's name, but then it's the person's name is in the name of the show, like Adams Hill Tonight or Hannah Gadsby Goes Domestic. I'm not as familiar with the rest of these people, but like some of these I'm like it's not great. It's not great, especially because we've, specified person entity. And this is where, it may be that some of the functionality for this in Python is a little better. This is totally workable and we can clean this up and we will clean it up, but I just thought I'd point it out that some of these things are still a little bit in flux. Okay, so I want to clean this up, and I mentioned before that I have some packages for identifying people's names. So I now want to just kind of quickly go and double check that what I have is what I expect to have. And so really quickly, I thought I might show you the baby names. The baby names package just sort of brings in this data set of baby names, and it's literally first names, gender, each year that name was used, and the number of people with that name in that year with that sex. And I think a proportion, I can't remember I think the proportion is specific to the year, but I'm not 100% sure about that. And I think this data is from the Social Security Administration. I don't really need the other 4 variables. I personally, I'm using this just for the name variable, but just so you know, this is, for me, a nice way to quickly figure out if I have people's names in my data set. And so what I'm gonna do is create a regex pattern that I call namepat, where I take the unique baby names, and maybe I can do something like that. Take all these names. I probably should lowercase them or something, but for now, this is fine. And I say, in my regex pattern, I'm saying, look for a word boundary, then the name, then another word boundary, and the collapse of the pipe means or, so that my ultimate pattern looks like this. And the reason I did this is just because the reason I specify the break is because Anna could be Mariana, or and especially there was one name in here called like Dear, D-E-A-R, which just happened to throw a wrench in the code, or D-E-A, I'm sorry, D-E-A. And I have one of the entities that extracted for Ali Wong was Dear Girls. And so I specified that it had to begin and end with a break so that D-E-A didn't get dinged as a yes name for the word dear. I don't know if that makes sense. Oh, just till 3 p.m. Okay, so I will very quickly not go, I'm gonna just take 5 minutes to just show you. I'm not gonna walk through all my cleaning steps. If you guys wanna look at that later, you totally can. But what I did was I just tried to clean up the list just to look for actual names, and then I made a network data set. So I have effectively like connections. So John mentioned Nick, Dave Chappelle mentioned Neil, blah, 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 blah. And when I go to actually create a network of these comedians and everyone they mentioned, I go ahead and create, maybe I needed to run this library. This is really crazy looking. So I apologize for that, and I will try to make this a little bigger. Okay, hopefully you can see that just a little bit better. and I'll try to walk you through it too. This is the Ali Wong set of nodes. Down here, I'm pretty sure it's Dave Chappelle. This is Trevor Noah, Hannah Gadsby over here on the edge, and then John Mulaney here. Apologies, this is really hard to read. But now you can start to see like Eddie Murphy is in common between Trevor Noah and Dave Chappelle. I think, I can't remember, there was another one. I think Jimmy Fallon is in common between Hannah Gadsby and John Mulaney. Apologies. The next step was going to be to create a little bit cleaner network. But hopefully this kind of gives you a sense of things you can do in text. And I will share the code of everything I went over today. But this was really the last bit anyway, was doing the networks. I also had some stuff you'll see at the bottom of the code that I send over. I also have some stuff for looking for keywords and entities using the Monkey Learn package. But yeah, if you guys have any questions or ideas of things you might want to try out, hopefully this gives you like a nice starting place as to what kinds of things can be done with text. And just inspires you to go out there and see what you can find. And I will stay on the line as long as you need. If people have free time and they want to ask questions or have anything, like I'm here and I'll hang out for a bit.